now we can actually talk about some more Monocro specific stuff, and by the end of this lesson, you'll actually be able to create some stuff on screen, which is pretty cool. Okay, so we are going to create some messages, but we haven't actually talked about animations, and you do need animations to make stuff visible. So for now, we'll just have to copy paste some stuff into as boilerplate, and then we'll explain it later on. So in particular, you might have to just copy paste something like this. And then just change circ variable to whatever mesh we want to show. It'll hopefully make more sense once we have a few examples. Okay, so just as some background knowledge, it is important to just know some general things about monochrome. Is the coordinate system. Coordinate system looks like this. We have 0, 1, 2, 3, 4, 1, 2. So this is generally the units that you're going to look for. Technically, if you want, you can kind of change it by moving around the camera, but by default, this is what it looks like. And the other thing to note is that we're in a right-handed coordinate system. So positive z is facing from the screen toward the person looking at it, right? Away from the screen. Okay. Other thing to note is that when a function asks for a color, it means a vector of 4 numbers. So there are some constants predefined. We can do, for example, red, clear, black, yellow, all that sort of stuff. But you can even do a custom one. So we can do 1, 1, 0, 5.1, 1, and that should give some sort of yellow color with a hint of blue tint. Okay, but yeah, you can probably survive with just using the built-in ones. Okay, now we can actually talk about meshes. So a mesh by itself is just a connected collection of dots, lines, and triangles. So you don't actually have to worry about it too much, but under the hood, this circle is made up of a bunch of line segments. This color grid is made up of a bunch of line segments on the border, and then a lot of triangles in the interior. Okay, and then each vertex has an associated color. So we can have primitive meshes, which are just meshes that we can create directly. There are vanilla meshes. So as a few examples, you have circle, tech, color grid, and then axis 2D. That's helpful in graphing scenes. Of course, there's a lot more. So you can find that in the documentation. Okay, but the other important thing is that we can have operators. So from these primitive meshes, we can apply operators to create more complex objects, and from some very simple objects through complex operations and through composition, you can get emergent phenomena. That's the idea. And the other thing to note is that everything on screen is a mesh. So there's not really a classification of this type of mesh and that type of mesh, or 3D meshes and 2D meshes, or maybe that text is a special mesh. No, everything is a mesh, which is very nice because it means that most library functions work with any type of mesh that you give it. Okay, other examples include rotated, centered, point mapped, X-stack. Again, I won't go into the details of every single one because I think you can go in documentation, but just some good ones to know. Okay, that's great, but more often than not, we don't want to just consider a single mesh, but a collection of them. So this motivates the definition of a mesh tree. So a mesh is a mesh tree, and a vector of mesh trees is a mesh tree. That might seem a bit technical, but informally, it's actually quite simple. It just means that we have a list of meshes, but not only that, that list of meshes can contain lists of meshes within them. So for example, we can have something like this, where it's a bit more intricate than a list of meshes, because we can have lists of meshes within them. Okay, I won't go into details about why this is useful too much, but if you're interested, you can read what I have over here. But the high level idea is that it provides a good sense of abstraction. Okay, and then whenever library functions say that input a mesh, more often than not, it just means mesh tree. I just abbreviate to mesh. Okay, and again, something more if you're interested, but not super important. Okay, here's a more complex example, and I think this is really good for showing a lot more of the how to actually use monochrome. So what we're going to try to do is create this scene. So if I'm thinking about how I can create the scene, of course, I mean, I already did it, but if I'm thinking about how I want to create this, there's 2 levels I'll break this down. For one, we can see that each individual picture here is very similar. So this motivates the idea that I want a function that'll be able to create an individual guy And then afterwards, I can use some operator, in particular this, to lay out the entire thing. So now let me just think about, how do I create this single cardioid? How do I create a single guy? Okay, well, I can make a function for that. I can make a function, it'll take in n, which is the number of lines we want, and then r is just going to be the radius. Okay, so now we have to think about, in a single cardioid, what do I have? Well, I have to have this border. So let me add a circle for that. And then I have to add a bunch of lines. So let me create this helper function. So that's another thing, is that we can create functions within functions. That's perfectly fine. And then for every single value we'll repeat this n times, where we'll basically create every single line and then add it to our return value. And then we have our entire mesh, right? Because we just have that circle, and then we have all the lines, then we're done. All right. So now we have to worry about positioning, but positioning isn't even that complicated. It's just, we have to arrange them, and then we have to place it wherever we want. So we're going to just use centered, and then xstack, and then we're good. Oh yeah, and then here's actually where we create all the cardioids, where you're going to just use the map function to simplify the calculations, but we could have used a for loop as well. Okay, and over here, this is just for showing it. Okay, so hopefully, of course, might definitely seem somewhat intimidating if this is just the first time you're seeing, but hopefully after breaking it down, it does look at least a bit simpler. Okay, now I just have a bunch of examples. I'll not go through them too deeply, but I'll just point out some interesting things. So over here, we're going to create a cocurve, and the point being is that we can use recursion. Yeah, we can use recursion. Other than that, it's mostly just about getting the exact positions right. Okay, here's one for the difference between two functions. This one's actually isn't too bad because there's a library function that pretty much just does this entirely, so we don't really even have to worry about it too much. Okay, here's Riemann rectangles. This function is going to help us with actually doing the rectangles. It'll take in the function and basically the parameters of the Riemann rectangle, and then it'll do all the calculations for us. Oh yeah, other thing I wanted to point out though is that notice how over here we can create a function and then we can call it as a functor. So user-defined functions and user-defined functors, they're very, very useful. Okay. One thing to point out that I will say is that this embedded space, it's very useful in graphing scenes. I might think of a better solution in the future, but for now, it's pretty useful if we have something that's typically in the global coordinate system, but now we want to force it into the coordinate system of this axis, for example. Okay, color grid from before, this is actually very easy because it's provided as a library function, but I will say color grid's pretty useful for a lot of things, so definitely a good one to know. We can do LaTeX, sorry. And this is an example of a 3D scene. So this is actually another reason why color grid is very useful, is that it provides a UV base, where point mount, what it's going to do is at every single point, so let's just look at this as our UV base, at every single point, it's going to apply transformation based on the user provided function. So there's going to be, in color grid, there's a vertex at all of these points, all of these in the integers. That's what distinguishes a color grid from a square, for example. And then if we apply a transformation at every single point, then we can create, we essentially have a parametric surface. So we can create some pretty cool stuff with that. So over here, I'm going to create a color grid, which is basically a checkerboard. And then I'm going to do a point mapped, which basically allows me to do a parametric transformation, and then we get the torus. Okay, this is a vector field. And the idea here is that there's a built-in field function. So I just have to say that given the pods, given the position, what mesh should I place over there? And what mesh should I place over there is pretty easy. It's just a vector. Now we do have to do some math to actually determine the color, which direction, how big it is, but that's all stuff that we can play around with. The overall idea isn't too bad. But again, the other thing I also want to emphasize is that notice that even though that this might seem somewhat complex, the actual interface for calling vector field is very simple. All right, this is possibly as simple as it can get. Okay, this is a tree. Okay, this one actually is a bit more complicated. This one is a bit more complicated, even though visually I guess it doesn't look that bad. The idea here is you have two helper functions, so we're gonna have one helper function for a tree and then another one for a node. So the actual node isn't too bad, it's just that we have a circle, a number, and then we're just gonna position them appropriately. The tree, you do have to, it is somewhat awkward, so if we're thinking about a tree, we first have to add in our current node, then we have to keep track of all the children trees, and then we have to position the children trees such that they're all in a line, and then we have to have the children trees in a line, so that's like all of these guys, we have them in a line, and then we have to make sure that they're below us, so we have to do another final stack operation. So it is a bit awkward, but not too bad at the end of things. Okay, there is also a way we can add edges, but that's probably more for a later lesson. Okay, and then finally we have a neural network. Again, this one isn't even that bad either. Just a bit of code, but not too bad. Okay. Okay, so here's a practice one. It's hard to say. I'm not sure how hard people would think about just looking at it, but at the end of the day, this isn't really too bad. You just have to do a bit of math, and you can do it using 3 operations. So how I would try to approach this if I'm a beginner is, okay, well, let me first try to get the placements right, and then let me get the colors. And then to actually get the placements right, think about how does this square relate to this square? And then how does this square relate to this square? And so on and so on. And then if you can get a relation, you can get all the placements right. And once you get the placements right, the coloring isn't too difficult. Okay. Again, the point of this lesson wasn't at all to cover every single mesh or every single useful one. I just want you to have the high-level idea of how can we compose meshes using these simple operators, and how can we define our own user-created functions to make some cool things. And if you have that intuition, that's going to be very, very helpful. That's what you really need to focus on.